Hello, my name is Shahriar Shahriari, and this is a lecture in a series of lectures on undergraduate mathematics. The topic of this lecture is strong induction and its connection with recurrence relations. The way to watch any of these videos is for you to stop the video occasionally and try to make arguments yourself. If I'm trying to prove something or if I'm looking for a pattern, you want to stop the video and try to do it yourself, possibly with paper and pencil at hand, and then have the video go on. Don't just sit there and listen as if I'm telling you a story. The principle of mathematical induction is a way of proof in mathematics. Usually what we have is an infinite sequence of propositions, all of which need proof. P1, P2, P3, P4, Pn, and so forth are an infinite sequence of propositions, all related to each other in some ways, but ones that need proof. If you want to prove these directly without induction, then I would require proving each one of those separately. And because there's an infinite number of them, that would take an infinite amount of time. So induction is a clever way to get around that problem. Instead of proving each one of them, you prove two things. First, you prove the first statement is true, and then you prove that if one of them is true, then the next one is true. Not any particular place in the sequence, but for any integer k, anywhere in the sequence, if you know the kth statement is true, you prove that from that you can prove the next one. If you can do that, then the two things together give you a domino effect. Since you've proved P1 is true, but you also have proved that if anything is true, the next one is true, then if P1 is true, P2 is true. But if P2 is true, then P3 is true. If P3 is true, P4 is true, and so on. All of them must be true. Another way of thinking about induction is the strong induction lens. Again, we have an infinite sequence of statements. You want to prove them one by one, starting at the beginning. You first prove P1, then P2, then you prove P3, and so forth. But when you're trying to prove the 47th one, you remember that you've already proved all the ones before that. So if you want to prove the statement Pn, you remember that P1 through Pn minus 1 were the earlier ones, and you've already proved them. In this way, you don't need to use just the one before to prove the next one. You can use all the statements before to prove the next one. This is what strong induction is. Let's do some examples. The first example is the following. Let's say that I have a large number of 3-cent and 5-cent stamps. What I want to do is make n cents worth of stamps on an envelope. For some n, I can't. If I want 4 cents, for example, from 3 cents and 5 cents, I can't make a 4-cent combination, but I can make it for some other ones. For which positive integer n is this possible? Induction does not help in finding the answer. What induction does is that after you found the answer, it helps you prove it. So I can't now say, okay, let's find the answer by induction. That's not going to work. What I have to do is think it through, figure out what the answer probably is, and then see if I can prove it using induction. I can definitely make a 3-cent stamp because I get 3-cent stamp, put it there. I can't make 1 or 2. Those are too small. I can't make 4, but I can make 5 because I have a 5-cent stamp. I can make 6 because I can put 2 3-cent stamps. I can't make 7, but I can make 8, a 3 and a 5. And then 9 is 3, 3, and 3, for example. And 10 is 5 and 5. 11 is 8 and 3. And 12 is 9 and 3, and so forth. And then if you think about it, after 8, you can make any combination of stamps that you want, any n cents worth of stamps. So you make a conjecture that n can be 3, 5, 6, and every integer greater or equal to 8. Now, this seems reasonable, and if you play with the 3 and 5-cent stamps, you will be convinced that this is true, that you can make any combination that you like, as long as that combination is either 3, 5, 6, or anything greater or equal to 8. But how do I rigorously prove that? And that's where induction comes in. In this case, I will use strong induction. What I want to prove again is that get exactly n cents using 3 and 5-cent stamps. N has to be 3, 5, 6, or any integer greater or equal to 8. By using just strong induction, I first do 3, 5, 6, 8, 9, and 10 directly. And we already explained how that is. But what about n greater or equal to 11? Stop the video and tell me if you have some number n that's greater or equal to 11, how are you going to make n cents worth of stamps? And here's where we use our inductive hypothesis. When we are trying to do n cents, we have already done all the cases before that. And all the cases before that includes the case n minus 3, which is 3 steps before. If I'm trying to create n cents worth of stamps, whatever induction told you how to make n minus 3 cents worth of stamps, add a 3-cent stamp to that, and you get your n cents. Because n is greater or equal to 11, n minus 3 is greater or equal to 8. But whatever it is, it's an earlier case that we have already done. This way of looking at induction is that you're starting from the smaller n and going up. At any stage, you're assuming that you've already done the ones before. By the time you get n, if n is 47, you've already done 3 before that, which is 44. How do you do 44? Well, we've done 41, and so forth, all the way till 11. 11, the one before that is 8, and those were among the ones that we had done directly. Whatever induction told you how to make n minus 3 cents worth of stamps, add a 3-cent stamp to that, and you get your n cents, and the proof is complete. What were the base cases? What did I need to do to get this argument started? Doing the right base cases is always crucial, otherwise your induction won't get started. In this problem, we use the n minus third statement to prove the nth statement. When we wanted to make n cents worth of stamps, we used the fact that we can already do n minus 3 cents worth of stamps. So we needed to go from Pn minus 3 to prove Pn. So whatever you want to prove, you have had to have done the case that was 3 down the line before it. This argument can't be used for 5 or 10 because 3 less than those are not doable. We can't make 2-cent stamps, and so we can't use that to make 5. We can't make 7, so we can't use that to do 10. So 5 and 10 are the ones that you really do need to do by hand. The easiest thing to do is to do 3, 5, 6, 8, 9, and 10 by hand as base cases. Why? Because you need those 3 consecutive numbers, 8, 9, and 10, so that you know after that, whenever you refer to 3 before, it's going to fall on something you've already done. And in general, this is always the case that when you do strong induction, you want to look at your argument. In that inductive argument, what did you use? And based on that, you will figure out what the base cases are. You can't really come up with the base cases without knowing what your inductive argument is. Let's do a couple of other examples. I want to use the Fibonacci sequence. So I'm going to define a sequence f0, f1, f2, f3, f4, and so on. This is a sequence of integers. f0 is 0. The first one is 1. And then after that, every one is just the sum of the previous 2. fn, the nth one, is the n minus second one plus the n minus first one. The 0th one is 0. The first one is 1. The next one is 0 plus 1. That will be 1. The next one after that is 1 plus 1. That will be 2. Then 1 plus 2 will be 3. 2 plus 3 will be 5. 5 plus 3 will be 8. 5 plus 8 will be 13, and so on. This is what's usually called the Fibonacci sequence, but I prefer to call it the Pingala-Fibonacci sequence. The reason for that is that Pingala was an Indian commentator who in 3rd century, 2nd century BCE studied this sequence in the context of the metric sciences, in the context of counting rhythms in music. The same sequence was also studied by Leonardo of Pisa in the 13th century. He has a problem in his book Liber Abaci that leads to the same sequence. Leonardo of Pisa is known today as Fibonacci, but that's not what his parents called him. His mom would not recognize if you said Fibonacci. Fibonacci is a name that his 19th century editor chose for him, and now he's known as Fibonacci. And almost everyone calls this the Fibonacci sequence, but I would like to call it the Pingala-Fibonacci sequence. There's a lot of patterns in the Pingala-Fibonacci sequence that you can find. When you find those patterns, induction is a good way for proving them. For this sequence, you can actually find a formula for it. In fact, I have 2 videos, one in the combinatoric sections under generating functions, one in linear algebra under applications of diagonalization, where we find the formulas for this sequence. But that formula is somewhat complicated and not really that helpful in finding patterns. I'm going to show you 2 patterns. In one, I will use just normal induction, and one I will use a strong induction to prove them. So here's the Pingala-Fibonacci sequence again. My question is, can you say something about the sum of their squares? What if you square f0, f1, f2, fn, and add them up? Can you say anything about that? Now, again, induction doesn't tell you anything about the answer, but will help you prove that pattern. We generate some data and see whether or not we see anything. This is not induction. This is just looking for a pattern. After we do that, we can see if induction will be helpful in terms of proving it. For example, when n is 0, we just have f0, and f0 squared is 0. If n is 1, f1 is 1, then f0 squared plus f1 squared will become 1. If n is 2, then f0 squared plus f1 squared plus f2 squared becomes 2. Okay, so what? Then we get 6 for n equals 3. For n equals 4, we get 15. For n equals 5, if you do f0 squared plus f1 squared all the way till f5 squared, you get 40. For 6, you get 104. And for 7, you get 273. So now the question is, do you see any pattern among these numbers 0, 1, 2, 6, 15, 40, 104, 273? This is not an obvious pattern, but let's think about this fourth one. f0 squared plus f1 squared plus f2 squared plus f3 squared plus f4 squared equals 15. Where does this 15 come from? Stop the video and try to see if you can see a pattern. You might notice that 15 is actually 3 times 5. So this 3 times that 5 gives me that 15. If you notice that, then you'll see that's a pattern that seems to continue. For example, this 40 is 5 times 8. The 2 is 1 times 2. 0 is 0 times 1. 6 is 2 times 3. 104 is 8 times 13. You might then conjecture that f0 squared plus f1 squared till fn squared is fn times fn plus 1. So this is a pattern that we see, and how would we prove that? So this is our claim. In induction, it's always very important to have your claim clearly stated, and n starts with 0 and goes all the way up to infinity. We prove it by induction on n. So the base case is when n is 0, f0 squared is 0. That's the same as f0 times f1 because f0 is 0. And so we're good with the base case. For the inductive case, we pick an arbitrary k. We say that assuming that we have proved the kth statement, let's prove the k plus first statement. So we assume that we already know that f0 squared plus f1 squared all the way till fk squared equals fk times fk plus 1. Remember, I'm not saying this is true. I'm saying if this is true, let's prove that the next statement is true. So assuming this, I would like to prove that f0 squared plus f1 squared plus all the way till fk plus 1 squared is fk plus 1 times fk plus 2. So if instead of n, I put k plus 1, I get fk plus 1 times fk plus 2. This is the statement I need to prove. That's the statement I get to assume, and that's the power of induction that allows you to assume something very similar to what you want to prove. Now, how do I prove this second statement? I can't write this as an equality and then manipulate it because it's not an equality yet. I don't know if it's true or not. So what I have to do is start with one side of it and get myself to the second side. So f0 squared plus f1 squared all the way till fk plus 1 squared, what is that equal to? How would I know? The thing to notice is that 3 dots means that there's a lot of terms that I didn't write down. And fk squared is the one right before fk plus 1 squared. And if I put these first terms in parentheses, I notice that those actually are the thing that my inductive hypothesis told me what it is. f0 squared plus f1 squared all the way till fk squared is fk times fk plus 1. So I can replace that fk times fk plus 1. So this is what I have. The fk plus 1 squared didn't go anywhere because I haven't done anything to it. And now from these two, I can factor out an fk plus 1. And so I get fk plus 1 times fk plus fk plus 1. Now I remember that this was the Pingala-Fibonacci sequence, and the Pingala-Fibonacci sequence had a recurrence relation, that fk plus fk plus 1 is the next one, and the next one is fk plus 2. And that's exactly what I wanted to prove. I proved that f0 squared plus all the way till fk plus 1 squared is fk plus 1 times fk plus 2, and that's what I wanted to prove, and so the proof is complete. So this was a usual proof by induction. In a previous video, we saw many more examples of this kind of induction. Now, I want to do another one for Pingala-Fibonacci numbers, but this time one where I use strong induction. What I want to prove is that for n greater or equal to 2, if fn is the nth Pingala-Fibonacci number, then fn plus 2 is less than 7/4 to the n. What do I mean by that? For example, f4 is 3. And so in this equation, if I want f4, n has to be 2. And so this will tell me, if it's true, that 7/4 squared should be greater than 3. And it is. It's approximately 3.06. Now, if n is 5, so that I get f7 here, I have to compare 13 to 7/4 to the 5th. I will see that 7/4 to the 5th is still bigger than 13. This continues as we go further up. This is not a very good upper bound for Fibonacci numbers. This is a proof of concept. I just want to show you how you would use strong induction to prove an inequality like this. We want to prove that f sub n plus 2 is less than 7/4 to the n for n greater or equal to 2. For base cases, I will do 2 base cases. We'll talk about why I need 2 base cases at the end of the proof. For n equals 2, we already looked at this. F4 is 3, that's less than 3.062, which is approximately 7/4 squared. For the second base case, I'm going to do n equals 3. When n is 3, I have F5, which is 5, and that's less than 7/4 to the third. So for these two cases, it works. Now, for the inductive case, I use strong induction. I will assume that the statement is true for n equals k and k plus 1, and I will use that to prove it for n equals k plus 2. In normal induction, you just assume one statement and prove the next one. In this case, I'm using two of the previous ones to prove the next one. And that's why I need two base cases. So I need n equals 2 and n equals 3. Using them, I can prove n equals 4. Then using n equals 3 and n equals 4, I can prove n equals 5. Now, the idea is that I'm assuming that for n equals k, the statement is fk plus 2 is less than 7/4 to the k. And for n equals k plus 1, if instead of n you put k plus 1, you get k plus 3 is less than 7/4 to the k plus 1. What I need to prove is that fk plus 4 is less than 7/4 to the k plus 2. I also will need this little fact that 11/4 is less than 7/4 squared. Just find 7/4 squared and you will see that it is bigger than 11/4. I want to show that f sub k plus 4 is less than 7/4 to the k plus 2. This is the n equals k plus 2 case. And I'm going to be using the previous cases of the same statement. I start with fk plus 4. Hopefully at the end, I will have convinced you that it's less than 7/4 raised to the power k plus 2. So what do I know about fk plus 4? This is the Pingala-Fibonacci sequence, and therefore I know that it satisfies a recurrence relation. Fk plus 4 is the sum of the previous two, fk plus 2 and fk plus 3. But fk plus 2 and fk plus 3 are exactly the ones that I know inequalities for by using induction. So my inductive hypothesis now says that fk plus 2 is less than 7/4 to the k, and also fk plus 3 is less than 7/4 to the k plus 1. That's the other inductive hypothesis that I can use. I've got to get them somehow to become 7/4 to k plus 2. I'm going to factor a 7/4 to the k from them, and I will get 7/4 to the k times 1 plus 7/4. And 1 plus 7/4 is 11/4. So I have 7/4 to the k times 11/4. Now I use that little curious fact that 11/4 is less than 7/4 squared. And so instead of 11/4, I put 7/4 squared and I get something bigger. And then these two multiply to the 7/4 to k plus 2, and my proof is done. Let's recap this proof for a second. I wanted to prove that fn plus 2 is less than 7/4 to the n for n greater or equal to 2. I had an infinite number of propositions to prove, P2, P3, P4. Each one of these for every n was something I needed to prove. And so I had this whole infinite sequence of things to prove. And the nth one is fn plus 2 is less than 7/4 to the n. That's what the pn statement is. So P2 when n is 2 is f4 is less than 7/4 to the second. P3 is when n is 3, that's f5 is less than 7/4 to the third, and so on. How did I do that? I showed that pk and pk plus 1, two of them imply the next one. And then we did the two base cases. That got the domino going and made us able to prove everything. Because I had these two, I now know that any two that I have that are consecutive, the next one must be true also. Since P2 and P3 are true, the next one is true. So that's P4. But now P3 and P4 are true. So the next one, P5 is true, and so forth. Again, I needed to know what my inductive argument is to know what base cases I need. Pingala-Fibonacci sequence was an example of a sequence given to us by a recurrence relation. By a recursive definition, we knew that everyone was the sum of the previous two. These kinds of recurrence relations work with induction really well. We already saw two proofs using them, and I will show you one more. In combinatorics, often we have a sequence of integers that counts something. And one way to approach that, instead of trying to find a formula, is to find a recurrence relation for it, just like the one for Pingala-Fibonacci sequence. If we can do that, then we generate data using the recurrence relations and then try to find a pattern, guess a pattern, and use induction to prove the pattern. I want to give you one last example of finding recurrence relations as an art to itself in a different video on recurrence relations in my combinatorics series of lectures. I will give you examples of that. Here I'm given the recurrence relation, but I want to prove whatever pattern I find using induction. I've been given the sequence. The first number is 1, the second number is 2, and then after that, you add, just like the Pingala-Fibonacci numbers, you add the previous two, but you multiply it by n minus 1. What kind of a sequence is that? Let's generate some data. A3, what is that going to be? Add the first two, 1 and 2, you get 3. Then what do I multiply it? I multiply it by n minus 1, which is 2. So I get 6, 3. What about A4? You add the previous two, that's the 2 and the 6, that's an 8. But now I've got to multiply it by 3 because n is 4 and n minus 1 becomes 3. 8 times 3 is 24. Let's do one more. A5. I add 6 and 24, and then I've got to multiply it by 4. I get 120. And the next one is 720 and so forth. This is my sequence. 1, 2, 6, 24, 120, 720. Have you seen that sequence? Stop the video for a second and think about that and try to come up with a pattern. Again, induction doesn't tell you what the pattern is. You've got to come up with the pattern yourself. If you think about it a while, then your guess might be that these are just the factorial numbers. An is n factorial. N factorial means n times n minus 1, n minus 2, all the way till 1. So 4 factorial means 4 times 3 times 2 times 1. That's 24. So that's my conjecture. And how am I going to prove it? I'm going to prove it by induction on n. Base cases, I'm going to do A1, that's 1 factorial, that's 1. And A2 is 2 factorial, that's 2. Those two work, and I'm going to need those two for my base cases because I'm using strong induction. I'm going to use the previous two cases to prove the next one. For n greater or equal to 3, using the inductive hypothesis, I'm assuming that I have already done the previous two cases. An minus 1, I already know is n minus 1 factorial. An minus 2, I already know is n minus 2 factorial. And I want to prove the next one. I want to prove that an is n factorial. How am I going to do that? I've got to start with an. I can't say it's equal to n factorial because I don't know if it is or not. I've got to prove to you that it's equal to n factorial. This is where the recurrence relation comes in. And that's why I said recurrence relations work well with induction, because the recurrence relation will already give you an in terms of the previous cases. I already know that an is n minus 1 times an minus 2 plus an minus 1. That was the defining relation for this recurrence relation. And now an minus 2, I already know is n minus 2 factorial, and an minus 1 is n minus 1 factorial. So this is ready made for me to use my inductive hypothesis. Instead of an minus 2, I put n minus 2 factorial, and instead of an minus 1, I put n minus 1 factorial. You might say, well, you didn't prove those. What I'm doing is assuming that if I knew two cases before, then the next one is true. If two cases are true, then I'm proving the next one is true. So what do I do here? I can factor out an n minus 2 factorial from these two, because n minus 1 factorial is n minus 1 times n minus 2 times n minus 3 and so forth. So n minus 1 factorial is just n minus 1 times n minus 2 factorial. So I can factor an n minus 2 factorial. From n minus 2 factorial, I'm left with 1. From n minus 1 factorial, I'm left with an n minus 1. And 1 plus n minus 1 is n. So this is n times n minus 1 times n minus 2 factorial. And that's exactly n factorial. And the proof is complete. And so is this lecture. Some version of these examples appear in two of my books, Approximately Calculus and An Invitation to Combinatorics. See you in the next lecture.